has some conceptual pieces, and it has some, we did do Bernoulli's equation.
Yes.
Okay. This is a continuity equation. So this question basically says, hey, you're in DC, there's a rainstorm, all of a sudden water starts shooting out of the manholes, you know, so many feet up in the air. What's the maximum height you can go up? Okay? And then finally, why in the movies is it so much higher? So there's conceptual pieces and mathematical pieces. Let's start with the first part. So we have this guy, as the storm drain has a certain diameter, okay? And then we have the storm drain cover. So this is, I call it area 1, I'll call this area 2, okay? And the fluid is moving in here with some initial speed, and it's going to leave here with some other final speed, okay? So there's a couple things, right? We have, first if we want to find how high it's going to go, we're going to have to know what the speeds are and everything else. So we start with the continuity equation. So when we do a problem like this, we're going to start with first the continuity equation. So we have the A1 V1 equals A2 V2, okay? We know the initial speed, we know the areas, so therefore we can find the final speed. So that means V2 is going to be A1 over A2 times V1. So V2 is, let's see, first area, 9.42, 3.14, okay. So this is 9.142 over 3.14 times V1. V1 was 4 meters a second. Yeah? This is 12 meters per second. Okay? So it's coming out of here at 12 meters per second. So the first thing we found is that the water coming out of here is going to be 12 meters a second, right? What will the speed of the water be exiting the drain? That's the question, right? Exiting the drain cover. So we just answered the first part of the problem using the continuity equation. Bada bing. Okay? The second part of the problem is saying how high will it go? So to know that, we have to use Bernoulli's equation. So we're going to say 1/2 rho V1 squared plus rho GH1 plus P1 equals 1/2 rho V2 squared plus rho GH2, right, plus P2. Okay, so the first thing you want to realize is that the flow inside the tube here has to equal the flow outside the tube there, according to Bernoulli, right? Now, what is going to be the pressure here? And what's going to be the pressure here? What's the driving pressure inside?
Bless you.
A lot of driving pressure inside is going to be the atmospheric pressure, right? Because it's just storm drain. It's a storm drain, right? And then the pressure right here is just this atmospheric pressure. So the pressures are the same. They go away. Nice. Okay? So now what we're going to do is we're going to simplify this a little bit. Another thing is you can assume is, what do we assume? We can assume that this height here is h1 equals 0. You want to do that? We can do that. Or you can say the difference is just the height. Let's just call it h1 equals 0. That's fine. Okay, so now we know V2, right? We know V2 here. So we can find this height. So we have, if we do this, we bring this over here, right? We end up getting a sign error, but it's not a big deal because we're doing it relative to the pressure because we're going up, right? We had done the direction properly. But anyways, okay. So we have 1/2 rho V1 squared minus V2 squared equals rho GH2, right? The rho's go away because it's the same density. Density hasn't changed. So now we have H2. H2 is going to be what? It's going to be V1 squared minus V2 squared over 2G. I don't know if you guys know this or not, but that looks like a pretty familiar formula. Only the signs have changed. It should be V2 minus V1, and then you guys should recognize we did this like first part of the semester. Anyways, so this is the height. And this height's going to be, in this case, we have V1 is 4, whatever, This guy was 4 squared minus 12 squared over 2 times
Yeah, I see it. Thank you.
1.8. Forget the sign for the moment, because it's doing it's a relative reference problem, so I won't worry about it. So this is 16 minus, so, right, so 144 minus 16 over 2 times 9.8, okay? So it's 34, 28, right?
Negative 6.53.
6.53.
Negative
Okay. Yeah, I mean, it's a negative sign only because of how we're referencing thing here. But if I fix that for you, it's gonna confuse you. So just do it straight out of the box, like nothing's wrong, okay?
So should we keep it, do we don't write it negative?
Yeah, I mean, from this guy's perspective, I'm going from here to here. So if I'm using this as my reference, it just, the way this is set up, I should have used a different reference for my height, but then the geometry gets messy. So anyways, it's gonna go 6.53 meters from my reference height, right? Or better way to put it is, it's gonna travel 6.53 meters is the distance it's gonna travel. If that makes more sense, okay? So it's gonna be 6.35 meters above this. So that's about 18, almost 20 feet in the air. Okay? That's high, but it's not like as high as in the movies. So you just answered the second part of the problem right here, right? How high will it go? Yeah. Blah, blah, blah. How high will it go? Okay? And assuming applied force is given gravity only, based on explaining how water supplies so high in. Okay, so see, it wasn't that hard. Part 1. Now part 3, you have to recognize 2 very important things. The driving pressure here, or the pressure difference, is 0, right? So therefore, it's not contributing to the height of this guy. But in a fire hydrant, where's the water coming from?
The ground.
No, it's coming from a big water tower. Okay? So basically you have a big source of water up here at some height. Sometimes it's 100 meters or more. So that means that the pressure here is going to be what? Remember, the change in pressure is going to be what? It's going to be rho GD. It's going to be really high. It's going to be much higher than atmospheric pressure, right? And the absolute pressure is going to be this plus 1 atm. Okay? So the point is that in a fire hydrant, the pressure coming in is coming from the water tower, which is much higher than the atmosphere. So that means that this equation here, if I was to write this back in this form, I would have my P2 would still be atmosphere, but this would be many times bigger. So this would contribute, right? So I rewrote it, so I'd have the 1/2 rho V1 squared minus V2 squared, right? Plus P1 minus P2, right? Equals rho G H2. And this pressure difference right here is what drives it, what causes it in the fire hydrant to shoot up so high. So this P1 is this guy here, which is driven by the water tower. All that pressure is pushing there. Remember when we did the fluids, right? We pushed it all down. So this is very high pressure, and it's being pushed out at that point. So not only do we have this guy, we also have the pressure difference, where it causes it to go up higher. So that's what you're explaining, but within formula and words.
Isn't B2 technically 0? Because the water stops at like reaches maximum height.
Okay, so this guy here, V2 is here, is when it's exiting
So what is the height in that equation?
This one?
H2.
This one? Yeah, this height, that's exactly why it's negative.
Well, it's negative.
Because what you're doing is basically, I mean, in reality, if you wanted to set up the geometry properly, you'd say it would go up a certain distance. At this point, the speeds of here is going to be what? 0. So that's why it looks like it's negative, because I'm using this geometry from here as V1, V2 for my continuity and Bernoulli's. So if I use Newton's, I'd use this speed to that speed. That's why it looks like it's flipped. You get it? Okay. But yeah, you're fine. Just leave it like this so we don't cause any undue confusion. Okay, so there you go. Is that clear? So what we do is we use the continuity equation to find just the output speed. We use Bernoulli's equation to find the height. and then we explain the difference in height because in the first part, there's no difference in pressure, but in the fire hydrant, there's a very strong difference in pressure. Okay? Okay, let's just see. What would the pressure difference be? So delta P would equal, density is 1,000, right? Times 9.8, times, in this case, D is 100 meters. Okay, what does that equal? Okay, 980,000. So of course, this is 9 times, this is 9 atmospheres, right? This is more than 9 times the 1 atmosphere of pressure. So 9 minus 1 is 8, so that means the driving pressure is 8 atmospheres. You see it? That's what causes it to go so high. Do you guys get it? You get the point or not? Okay, I mean, as you play with it, you'll get it. That's basically 4, okay? That's short answer number 4. Sorry, Mahadi, should have done that first. Okay? So, now we're going to go with 3. It's one of the longer problems. I almost feel like I should move this board. Okay, we have a spring. Okay, it's 9 newtons per meter, 2 kilogram mass. Displacement is given by this formula. Okay, so we have a spring mass system. Okay, this is K. The spring constant is it 9 newtons? Yep, 9 newtons per meter. Okay, the mass is 2 kilograms. And it's saying that the oscillation, the actual displacement, x, is equal to 12 centimeters, the cosine of omega t, right? Of omega t, okay? So I gave you the actual x, remember the explicit solution? We talked about this in class. This is the actual explicit solution for the spring, and these are the parameters. First thing it's asking for, I think, is what is the frequency? The displacement. Is this determine the angular frequency, the amplitude, the frequency period, blah, blah, blah. Okay. So, first off, we know if this is my displacement curve, what's the maximum value of this? The maximum value of this is when cosine is equal to what? 1, right? Cosine, remember cosine looks like this, right? So this is cosine. So it's 1 minus 1, 1 minus 1. So its maximum value is at 1. So when this equals 1, what does x equal? 12. So the maximum displacement, right, which is, it says, determine the angular frequency, amplitude, frequency, period, maximum velocity, total energy. The maximum displacement, or the amplitude, is 12, right? So we're going to say the amplitude is equal to 12 centimeters. Okay? That's the first thing we figured out. Next thing is we want the angular speed, or the angular frequency. Angular frequency, by definition, is k over m. Okay? So that means that we're going to have 9 over 2 square root. So it's the square root of 4.5, right? What is it? 2.72? 2.12? Okay, 2.12 radians per second, right? Okay? So that's the angular frequency, right? The amplitude we have. Okay, the frequency, on the other hand, the frequency is what? This is 1 over 2 pi times omega. Is that right? Yeah? So this is the 2.12 over 2 pi. What is it, like by 6, 23. It's like a 0.308 or something? Huh? Yo, you don't have a calculator, are you missing?
3.37.
3.37? Okay, I'll believe it. 3.37 hertz. Is it 3.376?
Yeah.
Well, then make it 3.38 then. Or 0.34. I'll swallow that too. So that's hertz, right? Under oscillations per second, hertz. Okay, and the period by definition is 1 over the frequency. So the period is equal to 1 over the frequency. Okay, so it's 1 over 0.3376, whatever, blah, blah, blah. Right? So it's like close to 4.
2.967.
2.967, okay, 2.97 seconds, okay? So every 3 seconds, it makes 1 cycle, okay? And then it says the maximum velocity, total energy, the moving mass, and blah, blah, blah. So, this guy right now, so far we've done all the definitions, right? The next thing we have to do is find, we have to find the maximum velocity and total energy. Well, let's start with the total energy first. The total energy we said is going to be when the potential energy maximum is going to be 1. It's going to be 1/2, thank you, K times the amplitude squared. It didn't equal 1. Okay? So, the amplitude squared, of course, is this guy, but this is in centimeters, so you want to be careful, right? So remember, if the energy is conserved, I can have the energy at maximum amplitude, I can have energy at maximum speed, or anywhere in between. Remember we talked about that in class. So this will be the maximum energy, right? So the total energy is going to equal to 1/2 times 9 times 0.12 squared, right? I don't know how many joules that is. 0.12. 0.0144,
0.0648.
0.06648.
48.
Okay. So this is joules, right? Okay? And then that's the total energy. And then if we want to have the maximum speed, we should the maximum speed, all right? So we know that the potential energy maximum is going to equal the kinetic energy at maximum, right? So this is going to be maximum and maximum. So this is my 1/2 K amplitude squared. It's equal to my 1/2 M V max squared. Okay? So I get rid of my 1/2. Now K divided by M is what? K divided by M is omega squared. So I can say that my V max squared is going to equal omega squared, my amplitude squared. So that means my V max is going to be omega times my amplitude. Okay? Which in this case was 2.12 times my amplitude, which was 0.12. Right?
0.2544.
0.2544 meters per second. Okay, so there you go. That's V max. Okay. That's it. That's it. So first thing you recognize in the spring system, we have simple harmonic motion, and we remember we had the total answer was A cosine of omega t plus B sine of omega t. This is the general answer. But in this problem, we gave you the explicit solution. Now, what I could have done, and may still do, is tell you, I put an amplitude, I pulled in an amplitude of 12 centimeters and let it go. And this is the mass, and this is spring constant, and then you gotta figure everything else yourself. So that means you'd have to actually solve for this thing yourself, instead of it being given to you. Which adds an extra step in this problem. This is supposed to be the hardest problem in the test, so I'll probably do that.
Quick question, why does the Vmax not have the V squared?
No, it had to be squared, but then I took the square root of both sides, right? Omega squared, square root is omega. M squared, square root is M. V squared, square root is just V. I just took the square root of both sides, right? So,
I did it the way, like, the top one with the squares. And
This one?
No, the V2 squared and
This
omega
one?
squared and amplitude squared.
huh?
But I took the square root of the final answer, I'm not getting that one.
Okay, well, because we already rounded this one, and you already rounded this one, so when you squared them, multiply them together, and then take the square root, you're gonna get a different answer. Right? I mean, if you take, you took this number, or you took this number?
That number.
Yeah. Because this is, I think this is rounded, right? Yeah? Okay, well anyways. But, oh, I mean, it looks about right, all right? So a tenth of more than a tenth, yeah. It looks about right. Okay, we're good? Maybe, kinda, sorta, kinda?
Yes, sir.
Fibber? No questions? Too soon, this is the first time you guys are seeing it, so. Okay, I did this one in class. Oh, what was the
It's my
medicine?
least favorite Vietnamese food.
Pho?
Yeah.
You probably know the real stuff.
I'm guessing here, so you guys gotta,
Probably the same thing as ramen.
50 cents. Okay, and then the radius is 0.5?
Color coded milk. Yeah.
Okay, glad you're all on board with me here.
We got your back.
Okay, so first thing you wanna do is you wanna look at this bad boy and you wanna say, okay, I'm gonna drop it overboard. Okay? And is it gonna sink or is it gonna float? So this guy, the way you know this is you have the density of the ball versus the density of the liquid, it's in this case is water, right? The density of the ball is greater than the density of the liquid, the fluid, then it's gonna sink. The density of the ball is less than the density of the fluid, then it's gonna float to some degree, right? And how much it floats is determined by the mass of the density of this, the mass of the displaced density. Remember what the definition of buoyancy was. In this case, the density of the ball is 5,063, the density of the water is 1,000, right? So definitely the density of the ball is bigger, so it will sink. Now you need to write more than this is bigger than that equals sink. Please, explain something.
That's exactly what I wrote my thing, so that's why.
What thing?
I know it's. Bless you.
Bless you.
Is that in your notes now?
3 exclamation points.
Do one
So you
more.
want to explain two on the test or?
I didn't get the point.
I want you to write explain on the test for extra points. Negative points, yeah, perfect. Okay, then what it's gonna do is it's gonna sink down some distance, okay, some distance d. At some point we believe, so this is part one. At some point we believe it is going to be neutrally buoyant. Now, that's an assumption. You know, it may be a material that, you know, the ocean's just not deep enough for it to be neutrally buoyant. It is possible, right? I mean, you could have a spoonful of a neutron star and you'd have about 1 million miles of ocean before it'd be enough pressure to hold up a spoonful of it, so. So the densest stuff in the universe is a neutron star, did you know that? Core of a neutron star?
Does it say something?
In a neutron star?
Oh, there's a neutron star. They said cell.
Okay, so what we've determined is that the pressure difference acting on an object is going to be the pressure created by the fluid minus the pressure the object exerts on the fluid. Okay? So this represents the pressure of the fluid, force over area, versus the pressure on the, from the fluid itself. Okay? It will be neutrally buoyant when that pressure difference is 0. Okay? So that means we make this equal that. So we can have the rho d equals the m0 g over a. Okay? And the g's go away. Okay, so we need the depth here, right? So basically depth equals the mass of the object, right, over the density. And remember, this is the density of the fluid, not of the object, okay? Quite a few of you are going to make this mistake and then come crying to me later, okay? This is the density of the water in this case. Are we clear? I'll say it in the morning. Okay, so this is 2,651 divided by 1,000 times. Now, for those inexpensive seats in the back, we have the surface area. Surface area of a sphere is 4 pi r squared, right? So that means this is going to be 4 times pi times r, which is 0.5, right? 0.5 squared. 0.5 squared is 0.25, that's a quarter. 4 times a quarter is 1. So I can clean this up, and this distance is then going to be 2.651 divided by pi. If you think that was magic, I got some really cool stuff I can say out of my car. .804.
I got .843 or
844.
.844. My bad.
Okay, so less than a meter underwater, this metal ball is floating. Okay? Now I want you guys to think about that next time you're jumping off a bridge trying to do a little cool diving. Very heavy objects can be floating in the water just under the surface. I don't know if you're in the class that I told it to or not, but I lost a friend to one of these said objects. Went down, never came back up. Well, he did, but he just wasn't alive when he did it. So, okay, so .844. Now, the last part of the question is asking, what happens now if I add a bunch of salt to the fluid?
Will it come out the object?
Well, salt's going to increase the density of the fluid, right? So if we look at part 3, let's say part 3 right here. So if we look at this formula right here, we have the distance equals m0 rho over a. If we increase the density by adding salt, right, that means this is going to get bigger. It means this is going to get smaller, which means this number is going to get smaller. Another way to look at it is that the mass of the object didn't change, g didn't change, area didn't change, but because the density is bigger, for these to be equal, right, if this gets bigger, you know, then this guy gets smaller, right? So in other words, the buoyancy force is going to get bigger. The pushing force one is going to get bigger, okay? So that you can explain that. I prefer to use a formula like this and say it'll be shallower, or just say the buoyancy force is increased because the density is increased. Did you get that, Odyssey?
One more time. One more time.
Okay, there's two ways you can explain it. One is that it will float at a shallower height because the density increases here, it makes this fraction smaller, which means my depth is shallower, right? The other way to say it is because I increase my density of the fluid, the buoyancy force becomes greater. You guys have to remember, what is buoyancy force? One of the definitions I gave you was buoyancy force is the weight of the displaced fluid, right? So if the density increased, that means the weight increased. So it means the buoyancy force is going to increase. You guys got it? Is that slow enough? What, again?
Can you write it down?
No, you couldn't read my handwriting anyway. It's all right. My head's got it recorded, although I don't have a Bluetooth thing from. Okay, so that's it. 1, 2, 3, bam. Pretty easy, right? Told you it's not a bad test. I told you guys that about 3 as well.
Well, like everybody failed the third test. Is that why the grades are high up or something?
Something like that, yeah.
Something like that. But it's up. Give him the money.
Wait, you think he's the only one with money in the classroom?
No.
Well, you can tell he's always smiling. That's usually a sign that you got money. Right?
Or you're on something.
Just so much smile.
The car.
I mean, do a social experiment. Walk around a big city downtown with a bunch of homeless people and look at their expressions on their faces.
What's it gonna be at?
Well, I'm not talking about the one that's like overdosed in heroin. She's laying there, you know. That's a different situation. I'm talking about this one. Like trying to explain to, well, Francis, it wasn't really like it sounded. She didn't mean it like that. She was talking about a joke.
You got that answer good. So.
Okay.
You got
Got you on camera.
So my friend in DC, she decides she lives above a lemonade stand. Okay, she probably maybe here. People are gonna start thinking, yeah, I know you guys have bad minds. Okay.
Wait, this is real story.
Almost all of my problems have real history to them.
Yeah.
So what did your friend do?
If you really wanted a lemonade, you can walk down there.
No, she wanted to just snag a bunch of it for free. She just wanted free lemonade, like unlimited lemonade. She wanted to sit there in the summertime,
You also
hanging
just
out in
run.
the garden.
Drink and run. Take your run.
Yeah, but that's harder. Now she can just like when he's not looking, just have a hose.
That's not conspicuous.
Hey, I didn't say she's a mastermind or criminal. Just that she wanted some free lemonade. I mean, don't tell me none of you guys thought about it. So, I mean, I know kids that try to hold up other kids with a little lemonade stand. So what are we talking about here? Okay, so what's happening is she's sucking on the straw as hard as she can.
Where did she get a straw of this size?
You can buy a rubber hose or plastic hose
Oh, okay. Well,
that's a mile long if you want.
So like a garden hose?
You can use a garden hose, but the diameter would make it very hard to suck. I mean, I don't know if you've ever, I don't know if you've ever siphoned gasoline from a car, but a garden hose is not the best choice. Just trust me on this one. Because when it starts squirting out, you end up swallowing a bunch of gasoline. You know, perfect face shot. Yeah. Jesus Christ. I swear to God. You guys are going to be the death of me. I swear. Nobody say that you don't have any entertainment in this classroom anyways. So what happens is you have the pressure that she's creating here, or pressure that she's losing here is the pressure upper, and then the pressure in the water itself, pressure lower. So as she's sucking the air out, what's happening is that she's reducing the pressure inside, right? But the fluid doesn't go up the straw or the hose because of the pressure she reduced. It goes up because of the pressure that's applied to it. The pressure is pushing it up, right? By reducing the pressure on top means you reduce how much is pushing back down. So it means it can raise up a little higher. That's what it comes down to. So let's assume for a moment, you know, she's what, 25 meters or 20 meters? 20.
That's tall, right?
So let's assume she's 20 meters, all right, 20 meters above the stand, okay? Now, she's sucking really hard, and let's assume that she can make this she's superhuman. Superhuman, she can make it 0 Pascal, right? Make it 0, okay? Okay, now I've been teaching this problem for freaking years. It wasn't until this class where I had any problems with it, okay? Just so you know. The applied pressure here is what? What's pushing down on the lemonade? Atmosphere.
Never mind. You said she's super.
Her sucking hand is pushing down on the lemonade. Okay. I think you had the geometry upside down, but it's okay. This is 1 ATM, right? The atmosphere is pushing down. So that means according to Pascal, you guys remember Pascal?
He was so old.
That means the pressure here and the pressure here have to be the same, right? Yeah? The applied pressure of the fluid is going to have to be the same. That's what he said. That's why we did the whole piston thing, right? Okay, so that means that the maximum pressure this guy could be is the pressure applied by the atmosphere. So this lower pressure is 1 atmosphere. And if she's superhuman, this pressure here is going to be 0. So that means that the pressure difference maximum you can have between here and here is what? 1 atmosphere, right? So you see the pressure difference between those two is going to be 1 atmosphere. And we said that before, pressure created by a column by a depth of water is rho GD, right? So we know the pressure difference here is 1 atmosphere. This is 1 ATM. That's equal. And let's assume that lemonade is water for all intents and purposes. So this is going to be water. Okay, let's just do, we'll solve this for D, right? So it's rho GD. Solve for D. So that maximum height that you can go is going to be 1 atmosphere divided by the density times the acceleration of gravity. Okay? So this is going to be 1 over 1,300 Pascal divided by 1,000 to the greatest per meter cubed times 9.8. I don't know. What is this, 10.7 or something? 10.3 maybe? I don't know. 10.3 meters. Okay? So the point is that if she was superhuman, it could create a 0 pressure difference here, or 0 pressure here, a full vacuum, then the maximum pressure this column of water can support is this driving pressure. And the driving pressure is 1 atmosphere. So that means the maximum height that this can sustain through just 1 atmosphere of pushing is 10.3 meters. That's the absolute maximum height that you can go up. And if she's 20 meters off the ground, she's never, I don't care how hard she sucks it, she's never going to get the water onto the thing. Okay? So, anyways, this is the absolute maximum. So this explains why. So that's the first part, is why can she not drink 1 drop of lemonade, okay? The next part of the question is, well, would it work for 10? Well, as you just saw, you know, 10 meters is possible because she knew a little less. Another way to look at this problem is to say, well, what would be the required pressure difference to lift it 20 meters, right? So we need, what would be the required pressure difference to lift it 20 meters? It would be rho G times 20 meters, right? So that means that we'd be equal to, what is it, 1,000 times 9.8 times 20, okay? So this would be 1,960 Pascal. Now that's a problem. This is the required pressure that would be needed for it to go all the way up the hose, right? And of course, the applied pressure is 1 atmosphere, which is much less than this. So she'll never be able to drink it just sucking on it based on atmospheric pressure. And it is possible from 10 meters because she's not human. It's not humanly possible to create a vacuum with your lungs. It's not possible. But it is possible to create, a reduced pressure. So we figure out a little bit less than 10 meters is possible because she could suck really hard and reduce pressure like this. It won't be 0. Okay? Right? What was the last part of it? So, to her just makes her explain why it's possible for reason, but it's possible. Okay, that's it. That's all there is to it. So this is a pretty easy problem, right?
So if she had like a straw with like a pool and a 10 meter area, then she could possibly.
Yeah. If she was at this height, she could definitely get something.
Right, but like if she had like a little reservoir or something.
Well, no, because, okay, so somehow you had to get to this reservoir. Okay, so somehow you had to get it up here, and then from there she could suck it. But how did you get it to the reservoir?
2 straws.
No, but then she'd have to be standing in the reservoir, sucking it up into the reservoir, and then going up to her window and sucking it out of the reservoir.